physics and entropy. So entropy is something that is talked about a lot in the various sciences, chemistry, physics, and is a big point inside of engineering. And entropy is basically a measure of the disorder in a system. So for every action or reaction, it takes it produces entropy. So entropy can only be created, but it cannot be destroyed. You can, however, displace it. So you can remove the entropy from a container, but you are still going to end up putting it somewhere else. So you can't destroy it, but you can sometimes move it around. Temperature and entropy are usually proportional, and entropy is measured in joules per Kelvin. And just to get a better idea of how entropy works, say for example you had a vase and you knock the vase onto the floor. That doesn't require very much work to be done. Even if you were to lift the vase up and to drop it to the floor, not very much energy would go into breaking the vase. However, to put the vase back together, it would require a lot more energy. And so returning something to its original state requires more energy than it did to take it apart, is the basic idea behind entropy. And that energy that you have to use to put it back together is still, it comes at a loss, is basically what entropy does. It's just a loss that has to be accounted for whenever you have an action or a reaction. And then entropy also follows what is called the laws of thermodynamics. So there is the zeroth law of thermodynamics, which basically states that if two systems are in thermal equilibrium with a third system, then these two systems must be in equilibrium. So this is a pretty basic idea. So that's saying like A is equal to C and B is equal to C. So A and B are our first two systems and C is our third system. Then these two systems must be in equilibrium. So therefore A equal B. Alright, and then the first law of thermodynamics states that heat and work, usually when you see those in equations, those are going to be Q and W, or W, are forms of energy transfer. And then the second law of thermodynamics states that the entropy of any isolated system not in thermal equilibrium will increase. So if you have a system, it's not in balance yet. In order to get into balance, it is going to generate entropy. So the same thing, every action and reaction increases entropy. And then the third law of thermodynamics states that entropy approaches a constant value as temperature approaches absolute zero. So in a pure crystal with no imperfections, as it approaches absolute zero, it would have zero entropy. And then to demonstrate some of these concepts a little bit, we have an example here of a man working in an environment at 32 degrees centigrade loses 2.5 kilograms of perspiration. Estimate the necessary change in entropy to vaporize this water. And then note that perspiration has a latent heat of vaporization of 24.2 times 10 to the 5th joules per kilogram. So our knowns here are the mass of water, which is 2.5 kilograms, the temperature, which is 32 degrees C, and because our problem needs to be done in kelvins, go ahead and multiply, or not multiply, go ahead and add the 273 to convert it into the Kelvin scale, which will make it 305 Kelvin. And then the the latent heat of vaporization, L sub V, is equal to the 24.2 times 10 to the 5th joules per kilogram. We are looking for the change in entropy, which is the symbol for that is typically an S, and so we're looking for the change, so delta S. Relevant equations to this will be delta S equals Q divided by T, and then Q is equal to the mass times the latent heat of vaporization. So for this we can actually go pretty directly. We can start plugging in a couple of numbers. So we have our mass, that's going to be 2.5 kilograms, and then we multiply that times our latent heat of vaporization, which is 24.2 times 10 to the 5th joules per kilogram. When you multiply that out and cancel your kilograms, you end up with 6.05 times 10 to the 6th joules. You can then take this and plug this into your delta S equation, putting your Q, 6.05 times 10 to the 6th joules. And with this, you can divide by the temperature, which is a constant, and that constant is 305 Kelvin. When you multiply these out, you will get an entropy, which will be 1.98 times 10 to the 4th joules per Kelvin, or written more practically, that will be 19.8 kilojoules per Kelvin.